And that should be all set up. All right, Yumi, you're up first.
Hi everyone, welcome to the morning session of the last day of Data Academy. My name is Yumi Choi. I'm an assistant astronomer at NOAA Lab and a member of the Rubin Community Science team. Oh. Okay, so this year's Data Academy, we're focusing on beginner level use of the Rubin Science Platform, RSP in short, and access to the Data Preview 1 data products, which are the real data, not the simulated one. And hack and new networking sessions are replaced with Q&A. As Melissa said, we have two drop-in sessions today, one after this morning session, and then the other one right before the evening session. And so if you have any problems and with the RSP access or questions about how to use RSP and Data Preview 1, please come to the Q&A sessions and ask your questions. And for this year's Data Academy, we have 10 sessions that are running morning and evening for a global audience. And the same sessions are repeated for a few times for maximum accessibility. So for example, we're covering 4 sessions today, but if you miss the other 6 sessions in the past couple of days, there are slides and recordings are available in the Data Academy website. So but we go through a couple reminders first. So the community forum, the community.lsst.org is a great place for you. If you have any questions or issues with the RSP usage and the data product. So you come to the support category and then make a new topic about your issues and questions. But the support category has the search functionality. So if you do searches with the keywords of your questions or issues, then maybe there is a old post from others have the same problems with you, and there might be a solution already. So that way you could find a answer to your question very quickly. But if you don't see any posts that are addressing similar questions or problems you have, please make a new topic with a descriptive titles. And if you provide some like detailed explains or context in the post with error messages is available, that would be super useful for us to reproduce your problems and try to come up with a solution as soon as possible. All right, and dp1.lsst.io is a documentation. You can find everything in today's session. It's all, informations about DP1. And there is also a project paper on the Rubin's Data Preview 1, which is under review and the project-wide review. But the current draft is available as a Rubin Tech Note, and it has a relevant DOI. So if you want to submit your science paper using the data sets, and please cite this DP1 paper with the relevant DOI. And general information about Rubin Observatory can be found in this rubinobservatory.org webpage. And under the For Scientists section, you can find a lot of useful informations. For example, like Rubin news, events, and other resources, and also some public outreach materials are available there too. And the Rubin data policy. So the data right holders are scientists, including students working or enrolled at US or Chilean Institute, and named members of the International In-Kind contribution teams. So only data right holders have access to proprietary data and RSP services. And you can see the list of international data right holders in this page. So what's the proprietary data? It includes like annual data release data products, images, and catalogs, and the prompt process images for 2 years. And those proprietary data is only accessible from the Rubin Science platform. But alert packets and the prompt catalogs and all the other data after 2 years, and all the documentations and support resources, such as the community forum, are public to everyone. Okay, so this session 4 is about catalog queries with TAP and ADQL. Don't worry about those terms. We'll get into those terms in the next slides. But this is what we're going to do in this session 4. First, we go over some key concepts that are relevant for the TAP and ADQL. And then we're going to learn how to do TAP queries using ADQL by going through some relevant notebooks tutorials and also cover some photo tutorials. All right. So key concepts, TAP stands for Table Access Protocol, which is an international virtual observatory alliance standard, and that provides a standardized access to catalogs. And the TAP provide the server-side filtering, which means that you can do all sorts of filtering on the server and then just retrieve the results. So you don't need to do anything on your local computer, and that minimize data transfer. And we can also do joins and cross-matching between the big tables on the servers, not on your local computers, and then retrieve the result you want. And TAP is really doing well with for big data, so it's scalable and for big surveys. And also it provides a reproducible workflows. So if you share your queries with your collaborators or post that in put that in your publications, anyone can use the same queries to TAP service and then have this exact same result what you had. Okay, and then TAP also works both in the portal and the notebook aspect. So that's really kind of a complementary functionality to each other. And then there are many more advantages of TAP services for large surveys. And ADQL stands for Astronomy Query Data Language. And this is also an IVOA standard for querying astronomical database. And it's based on the SQL. And it's a standard across virtual observatory services. So you learn just one language and then applies to other survey data if they are registered at a virtual observatory. Okay, and then other key concepts is TAP schema. TAP schema is the set of the tables that describes the data tables and their columns. We're going to look at the examples, what this exactly mean. And query means a string formatted in ADQL that selects data from a table with constraints if desired. So basic components of the ADQL query are select from where. So this is the basic format. Select columns from your catalog, whatever catalogs you want, where this provides constraints you want to apply. So here the columns are is a comma-separated list of columns to return. And the catalog here is the name of the catalog to retrieve data from. And constraints is only, is to return only rows with column values that meets the constraints provided. So generic like form of the ADQL query statement is like this. Select column 3, 4, 5 from my survey data table, where column 1 is greater than 0.5 and column 5 is less than 10. Right. So before moving on to the notebook tutorials, so we're gonna use some data products in the example notebook tutorials, but it's not gonna be covered in this session. But session 7 to 10 cover all different type of DP1 products. So please check their slides and recordings if you are interested in learning more about those data products. Okay, so now we go to the notebook tutorials. So if you go to the data.lssc.cloud, then this is the RSP. And I already logged in, and then you click the notebook aspect and it will start up a server for you. Okay, so and then lead to the landing page, which has some useful links to the data releases and resources. But if you click the tutorials tab, and there is DP1, and under 100 level how to use RSP tools, if you go to catalog access, then there should be a get started with tab. So click this one. And in this notebook, it shows how to use tab service efficiently. So we kind of covered this introductions. So we just import the packages we're going to use in this notebook, and then instantiate the tab service. And first, let's explore the tab schema. So we said tab schema is a table of all the, so you can think of this is a map, what's available for the DP1 on RSP. Okay, so first, list all the schema. So we're gonna select everything from tab schema.schemas. So this will list all the schemas available in through RSP. So you can see there is a DP 0.2, the simulated data, and DP1 data sets as well, and schema, and the IVOA schema and tab schema. So we just convert this result to the table, astropy table, then it will show the result as a table. Here, before we move on, we are briefly talk about asynchronous query. So there are two types of query you can do. First one is asynchronous, and the second one is asynchronous. So the basic recommendation is to use asynchronous queries all the time, but only cases maybe for querying table schema, which is really super quick and super fast, then you can use a synchronous query. So synchronous query is just running your query right away, like service.search. So and pass your query statement. That's a synchronous query. And the big difference between synchronous and asynchronous query is that for the synchronous query, you have to wait until the results are returned. And the meantime, the other cells you cannot execute. But with the asynchronous queries, once you submit your job and then the job is running in background on the servers, but you can continue to execute other cells, like making plots. So that's good. But for the step schema service, we can use synchronous things, but this is very quick. And so now we know there is a TP1 schema is available. So let's look at what kind of tables available in the TP1 schema. So this is like select everything from tab schema tables where the tab schema name equals TP1. So let's do this query and get the result. See, this is super quick. So under DP1 schema, there are 12 tables we can use in the through RSP. And DP1.object table, source table, forced source table, DIA object table, DIA source table, force source on DIA object table, and coed patches table and visit, CCD visit, MPC orb, SS object, SS source table. So these are all available tables for DP1 on the RSP. And then if you want to look at what columns are in each table, then you can select column names and data types for each column and description of each column and unit of each column. And from the schema, the columns where table names are equal to object. So we're gonna retrieve all the columns in the object table. And we can print out result. So there are 1,296 columns. So you don't definitely want all the columns in the table. So you need to figure out which columns you need for your assignments. But this is a good way to figure out what columns available in each table. All right. And we're going to talk about best practices for tag queries briefly. So as I mentioned earlier, use asynchronous queries all the time, except for tag schema querying. So for the asynchronous queries, you have to define your query statement first, and then submit that as a job to the server, and then run that job and fetch the result. So this is let the servers do all the work for you in the background, and then you can fetch the result and then only retrieve the result. And on the disk, the database is stored, divided up by like spatial regions. So if you are querying the table that includes the sky coordinates, then the recommendation is to use a spatial constraints, because the database is divided up based on the spatial regions and then distributed across multiple servers. So if you do spatial constraints, then it will only search a small number of servers that contains that part of the sky area. So it doesn't look at all the database across all the servers. So that makes your query faster. And for the spatial constraints, you can do either cone search or the polygon search. So for the cone search, you can execute your queries with where statements using the constraints in points and circles. So here the points gives you past the catalogs column names for the sky coordinates. So for the object table, it's coord_RA and coord_DEC. And circle, you define the search radius with the center position of the search coordinate. So you defined a small search radius circles of your search, and then contains ensures that only return the rows that meets the the constraint statements is true. Right, so here is the example. So we retrieve coordinate informations from the object table around this central coordinates within 0.01 degrees. So this is your query, and you sum in your job and run the job, and then once it's completed, fetch your result. Okay, so it's completed and then return 141 rows that match your constraint, spatial constraints. But you can do like polygon shape, which is more complicated shape you want. And then you can replace the circle function here with the polygon function. And you just provide the pairs of RA and DEC corners of your polygons. Right. And then inside a query, you can sort the results using order by. This is sort your results by the columns you designated here. You can also sort like ascending order or descending order. But here we just we do the same queries, but return the sorted result. So this is what this query is doing. But order by is means that there is an extra step after filtering all your results and then sort. So it's if this is not necessary, then you can skip this part. And then there is top function, which allow you to limit the row number. For debugging and testing queries, people sometimes use this top, to return like top 10 rows of the search results. But recommended way for debugging and testing queries is to restrict the number of, is not to use the top, but just use use very small spatial regions, which is much faster than top, because top requires extra steps. Like once you retrieve all the data and then you figure out, extract the top n rows from that. So it requires extra steps. All right. So this is a basic how to use like tab service. So the general recommendation here is use the asynchronous query if possible. Only use case for using synchronous query is for the tab schema. And then use the spatial constraints if that's possible for your search, which makes your query faster. Okay, any questions? Great. Then let's move on to the next notebook, which is about parallel queries with tab. So in this notebook, it shows how to execute complex ADQL tab queries on catalogs. But we covered a lot of the basics of the ADQL. So we'll jump straight into the tutorials. So we import packages and instantiate the tab service. And then we're gonna try to manipulate columns. So this is the basic queries we have, like from the object table, select these columns. If the coordinates are within this small searching circles, right? But what we can do is rename columns. So for some reason you don't like coord underscore RA or coord underscore DEC or other column names, then you can just change it to a simple one, RA and DEC. So you can do that. Select this column as RA and select coord underscore DEC as a declination, DEC. And then do the search and submit the job and execute it and then fetch the result. So when you look at the result column names, now it's RA and DEC instead of chord underscore RA and chord underscore DEC, right? And then you can also apply ADQL functions inside your query. So for example, there is the radians function, which converts your coordinates in degrees from degrees to radians. And then there's this distance function, which computes the angular separation between all the coordinates to the center of the search circle. So this query will return RA and DEC in radians because we use the radians function, and then also return the distance angular separation between the points, each point, and then the center of your search coordinates. And also, in many tables, we have fluxes, all sorts of different types of fluxes. And then we want them in magnitude in some cases. So there is a function called psi SQL underscore nanojansky to ABMag for converting your flux to magnitude, and psi SQL underscore nanojansky to max sigma, which convert your flux error to magnitude error. And in the object table, for example, PSF and C model fluxes have the corresponding magnitude columns, but other fluxes like the Sersic flux doesn't have pre-computed magnitude columns for it. So we have to use this function to convert flux to magnitude. So we pass this query to job tab service and run the job, and it's completed. And you can see this is the Sersic magnitude and Sersic magnitude error columns provided for you. And one thing you notice is that the different precision, so pre-computed magnitude columns are 32 bits float. But if you compute the magnitude using this psi-SQL functions, that returns the 64-bit float. But in practice, this precision difference shouldn't be a matter, but depending on your science case, this is one thing you have to keep in mind. Right. And then you can also derive and define new columns inside query. So for example, you want to make a color magnitude diagram or color diagram for your object, but then you need color columns, right? So you can do either just retrieve the magnitude informations on all different filters and then retrieve the result and calculate the colors from there. But also we can do inside the query. So in the query, now you calculate the U minus G, G minus R, all different color, and then save that as a new column, UG underscore column, this kind of thing. So you compute and predefine a new column inside the query, and then submit the job. And if you look at the result table column names, now you have UG color and G minus R color, R minus I minus Z, G minus Y colors. So it's available for you. So you can just use this result table right away. All right. And then there are other constraints we can apply to the columns. The first one is relational operators. So in this query, we are selecting coordinates and the color informations from the object table if the sources are within this search circles, but also if their magnitude in all filters are less than 25. So this makes sure we're selecting the bright object, the object that are brighter than 25th magnitude in all filters, and we retrieve the coordinates and color information for those objects from the object table. So this is the result. This is the query is completed, and then we can just look at what's the mean and max values of the derived columns for this bright sources. All right, and then we can also apply operators to functions. So we saw already like size equal SQL underscore Nanogensky to ABMag thing already, right? And then we save that column as G Sursic magnitudes. And then using this newly defined column in your constraint as well. So no, you cannot use this. You have to use always the original column names in the constraints. So this is the right way. Sorry about the confusion. So in the where statement, again, you have to use the original column names to apply your constraints. All right, so this also, we can submit a job, run, and fetch the result. And we have 44 results, which meets the G-band Sursic flux is brighter than 25. Okay, so we can delete the result. And then within the where statement, we can also use between and statement. But if this is about the sky coordinates, please don't use between and end. For example, like RA greater than this and less than this, that kind of statements. The tab service do not interpret that as in the same way as the cone search or polygon search, the spatial searches we saw in before, and it also less efficient. So using this between and then statements for the coordinates. So for the coordinates, please don't use this between and statements. But if you have something like, okay, so I want object that are brighter in G band than R band and brighter in R band than I band. So in the energy spectrum, you can, this is like blue object spectra. So the flux density decrease with wavelengths. So this is selecting only like blue object. So your query is like select object ID and the GRI PSF magnitude from the object table if the source are inside the search circles, but only if the meeting this criteria. So R band magnitude should be between G and I band magnitude, and we submit the job and run and fetch the result. And it returns like 3 examples. And when we print out their object table, object ID and GRI magnitude, you can see they are very only slightly different, but they are meeting this criteria we asked. Okay, so there is a where in statement. So if you want to select the rows that particular columns are in a list of your interest. So let's say there is, so we said we have the object ID list from the previous example, and just define the ID list as a string, formatted as a tuple, and then using this information in our query. So this query is now saying is about like select object ID and sky coordinates from the object table if object ID is in this list. So we are submitting the job, run the job, and fetch the result. And if we look at the result, this is the thing. So this should match the result exactly like this, right? The same object ID. Okay. Any questions unanswered in the chat? There. Okay, if not, then we can keep going and now look at the table joins with tab. So so
Sorry,
far the
if I may ask a question. So actually Jeff was kind of answering to my question, but so I was wondering about the coordinates. So these are ICRS, right? So they
Yeah.
are at the time of the observation.
Yes.
Yes. So do you have a little Python script to convert them, for instance, to J2000 or other commonly used coordinates in so when you want to cross-match, for instance, with other catalogs?
Mm. I think we can use SkyCoord package to do that. AstroPi SkyCoord.
Okay, thanks. I'll look.
Yeah. And in the portal, also you can, so it's a manual way, but you can select the coordinate systems you want to display. And so you can compare two coordinate systems on one screen, like equatorial versus galactic, that kind of thing. But SkyCoord package should do that for you. But I'm not sure there is a LSST in-house functions to do that.
Okay, thanks.
Right. Okay. So far we only look at the tab query examples, just retrieving a data from one table. But in many cases, you want table joins or cross matches. And this notebook show how to do table joins in the query. So basically, the generic example is that there is a table one and then table two, and then they should have a common columns in both table, and we join on that column, that common column in both table. So table one ID and table two ID, that should be a common column between the two table, and join them on that column, and then retrieve whatever columns from either table one or table two can be selected, and you can retrieve the result. So we import the package and define parameters first. And this, so one use case example could be, let's say you have a variable stars, you want to make a light curves, then you need like magnitude information or flux information at each observation, and also the time of each observation, right? And so from the forced source on DIA object tables, we can get the filter information and the associated flux measurements in those filters. And then from visit table, we can retrieve the exposure midpoint MJD, the observation time. That means we need a join these two tables to get flux information and band information over time of observations. So we have common column in these two tables, which is visit identifier. And then for this example, we just pre-select a source with DIA object ID. So we submit this query, run the job, and fetch the result. And this is the columns in the result table, band, PSF flux, and then the MJD of observations. And this plot shows the light curves of this variable source. And then the other use case example could be the moving object. So you want to know the X and Y position of the moving object over time, right? So from the SS source table, we can get the heliocentric X and Y positions. And from the DIA source table, we can get the midpoint MJD of those source, those moving object. And then there is a common columns between the two tables, which is DIA source ID. So we use this common ID information, retrieve X and Y from SS source table, and then the time information from the DIA source table. So this runs the query, and then this is the result. So we have X, Y, and time information in the table, and then we can plot their positions and color coded by the relative time from the first epoch. So the object is moving this way over time. All right, so do we have any questions before moving on to the portal aspect? If not, let's continue. I have like 6 more minutes. So basically, we can do pretty similar things in the portal. So if you go to the portal aspect and then select the DP1 catalog, you can see the table collection, the schema. And then if you select the DP1 schema, then it all lists available DP1 tables here. So we can select object, and then you can do spatial searches here. This is a default center coordinate we can use for the search search, and then set the searching radius here. You can change the units as well, and then select the columns you want, and just to search. This is portal thing, but if you go back to the catalog page and then click the populate and edit ADQL, then this will populate ADQL queries for you. So if you're not familiar with writing your own ADQL queries yet, you can do this practice and see how the query is constructed based on your selections. But if we go back to the slides, and then, maybe I can show, I want to show one more things. So if we go back to the UI assisted things, and then let's say there is a Swaggle Math EBV minus value thing, but if we want to select only rows that with the reading is less than 0.01, and then you click the populate edit the ADQL, then you can see in the where constraint, this constraint is also applied. So this way you can play with constructing the ADQL. And you can also do like 2 table joins in portal. No, this is the simple one, where we can go into the next slides, and I can copy the queries here, and then you go to the ADQL query and then just clear, and then paste your query for 2 table join, and then you can click the search button, and this will give you the joined table result. And if this query is not take too long, but I can show in the next example. So we go back to the ADQL examples. Oh, sorry. And then do the three table join. This is a query example. And if you clear and then paste that new query and then search button and the job is sending, and if you can click the send to back, then in the job monitor, you can fetch the result when the job query is completed, and then click this show results icon, then it will pop in your results tab. So you can explore that way. But if your query takes long, you can send the job back to background, and then you can monitor your job status and then fetch it when you are ready to use it. All right. And then so in the result table, last thing that I want to show is that, so this is the result table, and here under the lamp icon, there is a use table as an unload to tab search. So click that, and if you go back to that, it will automatically lead you back to the catalog tab. Oh, you're the multiple tab, because I was using this before, I think. Right. But anyway, so now you can see the result table is unloaded, and then use them as a input table. And then you can join and cross-match this table against whatever available in DP1 tables. So this is the unload table, which has the RN and DEG information. Then you want to do like spatial search against the object table again, and then just select coordinate and the EB minus P values. And this will do join between your unloaded table against the DP1 tables. All right, so this is doing the job, and you can also send this job to background. But last thing that I want to point is that there is a multi-archival tab. So you can select what kind of tab you want. For example, there is a Gaia tab or Nuala tab, or whatever your favorite tabs available from the virtual observatory. And then you can select what kind of table you want to cross query, and then retrieve the result table, and then use them as an unload table for join against the DP1 table as well. So yeah, that's possible. And as I'm at 50, I'll stop here and take any questions. Yes. The current limit for the result table is 3 gigabytes, and for the unloading table is 32 megabytes. Is there any questions that I missed in the chat that has not been answered? Probably not. Right. Then we're gonna have like 9 minutes break and then come back for the next session.
I don't know, Yumi, if you can stop the recording, but I think that we are starting and stopping recording per session, right?